Okay, so what I want to look at in this lesson, I want to continue to look at light, and we'll start to introduce, we'll finish off a little bit more of the emission spectra, but then we also want to start to look at absorption spectra. So just before I do that, we want to talk a little bit more about um, electrons and them being excited. So if we take here, okay, so what we have here, and I'll just color this in. So we have the nucleus here, and then we have these energy levels, okay, or orbitals, spaces where electrons can hang out. Now, if we take, so imagine then we have, so let's say this is an electron here. So we have this electron just here like so. So we have this electron. What will happen is when this atom receives a certain amount of energy, so for example, you could get light or energy will come in. And that light or energy, you can think of it like a wave, or you can think of it like a particle, like a photon of light. And it has an exact amount of energy, okay, related directly to its wavelength. And what will happen is, if it has the right amount of energy, it will excite this electron. So this electron will absorb the energy and become excited. And what it'll do is it'll move up to a higher energy level. So it'll move, let's say from here, it'll go up to this energy level, and it'll hang out up here for a period of time. So it'll get excited. And then once it's there for a sufficient period of time, what will happen is it will actually come back down. So it'll fall back down, and it'll come back down to its resting state. And when it does that, it will emit a wavelength or a particle of light. Okay, so the light that it gives off will be equal to the energy that was put in. So for example, the wavelength that comes in here that excites the electron up to this first energy level or this first orbital, when it drops back down, it'll re-emit that light. Okay, now what's really important as well is that the amount of energy to get, for example, the electron to move from this energy level to this energy level is very, very exact. So if you had, let's say, there's a photon of light or energy that came in that didn't have that exact amount of energy, it wouldn't have any effect on the electron. It wouldn't cause it to go up to a higher energy level. It'll just pass through. So what you can say is that, like let's say between, so for an electron to move up to this energy level and then come back down again, there's an exact amount of energy that will make it do that. And also as well, if the energy level moves up to this second energy level and falls back down, again, it's a different amount of energy that is needed in order to get the electron up to this higher energy level. And this is really these energy levels, let's say, that electrons can move up into and then drop back down and give off light. This is what kind of accounts for the different colors that we see. So we have this, this whole spectra of colors, and that can be directly related to the energy levels that the excited electron moves up to and then drops back down into. So, like, what's really important is that if you have an electron, like let's say the electron is here, it will not move to this higher energy level unless there's an exact amount of energy that's hitting it. Or another way to think about it is unless there's a wavelength that's exactly matching the energy that it takes to move it up to here. If it's too small or too little, it won't actually move it. It won't have any effect on the electron. And that's why you can say that these are quantized. Or another way to kind of think about it is it's also what's known as like a quantum leap. So the electron leaps up into this higher energy level and goes back down again. And these energy levels are, let's say, when the electron moves up to this energy level, let's say, and then drops back down again. These different energy packets that are needed in order to do that, first of all, needed to excite them up, and then what the energy that they gave off, these can be directly related to specific wavelengths of light. And as we know, these specific wavelengths of light can be specifically can be linked back then into the different colors of light that we see with our eyes. So, and that can be related directly into the movement of electrons into higher energy levels and then back down again. So if we think about different atoms then, so we know that we have different elements can emit, so it can give off different wavelengths of light, and that's directly linked to their electronic configuration. So if we take, for example, like this here is hydrogen, so we can see here that the atoms of hydrogen, for example, the electrons in that atom of hydrogen, it can be excited up to different energy levels, and when it falls back down, it gives off these different wavelengths of light. Okay, and that's related directly to the electronic structure. So, for example, here we can see, it gives off light in the visible spectrum. So atoms can give off these different wavelengths of light within the visible spectrum, and that falls if you take the whole electromagnetic spectra or range that we have. We can see here that electromagnetic radiation that has a specific wavelength, for example 700 nanometers, that directly correlates to the color red. So atoms such as hydrogen, they can give off when they're energized, the atoms can give off wavelengths of light that are within the visible spectrum. And these atoms of light that are given off within the visible spectrum, these are what are known as the Baumer series of the Baumer series. So if you like, this here is these are the bands of light that are given off, not necessarily by hydrogen, but just so you have atoms, and they can give off these wavelengths of light that are directly related to the visible spectrum, and they would be known as the Baumer series. So it's kind of like the energy it's given off is directly related to this the visible spectrum. Now, not only that, but atoms can also give off wavelengths of light that relate to the ultraviolet region. So if we take, for example, if we have a look here, so just up above the visible light spectrum, you have this ultraviolet spectrum. And within this spectrum here, we can see that the wavelengths, okay, so or the distance between, let's say, here and here, is shorter than it is, let's say, within the visible spectrum. So these ultraviolet rays of light, for example, or electromagnetic radiation, have much more energy. But atoms, for example, like hydrogen, they can also be, the electrons can be excited up into really high energy levels, and then when they drop back down, they give off this higher energy electromagnetic radiation within the ultraviolet region. And this region then is what's known as the Lyman region. And this is because this was discovered by this guy who discovered it at that time. And also as well, not only can like atoms such as hydrogen give off, for example, ultraviolet radiation, but it can also give off infrared radiation as well. Now we don't detect these with our eyes. We'd need special instruments to be able to even detect these wavelengths of light. But our vision is based on this very thin band of electromagnetic radiation, which is the visible light spectrum, and that is directly related to energy coming in and exciting electrons, them moving up into a high energy level, them dropping back down, and then them giving off that energy that our eyes then can kind of pick up and see. Now, what we can get, so we talked about, so these are emission spectra. So this is like, where if we have, so remember you have like a container like this, and it contains, for example, hydrogen gas, or discharge tube, we energize it, so we can put electricity through it. The electrons get excited, they give off this radiation. That radiation is passed through a prism. The light is diffracted at different angles depending on its wavelength, and then what happens is you get lines, let's say, on a spectrum, something like this. So this is what's known as a line emission spectra. Now, what I want to talk about then is not only do atoms emit light, but atoms can also absorb light as well. And this here is what's known as an absorption spectrum. Okay, so you can see here that we have all of the spectrum of light, going from red all the way over to purple. But you can see here that there's some of the wavelengths of red light is absorbed, some of the wavelengths of yellow light is absorbed, some of the wavelengths of blue and purple are absorbed as well. And this here is what's known as an absorption spectrum. So if we think about this then, like what's actually happening here. So what we can do is if we take our light source, so remember this is white light and it contains all the wavelengths of light within it. So if you pass this white light through a prism, what's going to happen is all of the different wavelengths of light are going to be diffracted at or bent at different angles, and what you will get then is you'll get this continuous spectrum like this. Okay, so it contains all the wavelengths and it's just spread across like this. Now, if we take, for example, if we provide energy, so we take atoms and we turn it into a gas, for example, and then there's energy, that gas is heated up. What's going to happen is the electrons will get excited. They will give off wavelengths of light. When you pass those wavelengths of light through a prism, what will happen is they'll get diffracted, and then you'll only get these very distinct bands that are formed. And this is what's known as an emission spectra. And this is very much related to the atoms that are present within it. So this is energy that's coming. This is this light or energy that's coming off these atoms only has certain wavelengths of light, and those wavelengths of light, or this emission spectra that it produces, is very characteristic of the individual atom that make up, for example, in this case, the hot gas that's given off this energy. So then you get this kind of an emission spectrum. Now, another thing that can be done then is if you were to take this same gas, for example, and you don't heat it up, so basically the electrons within the atoms within the gas are not overly excited, so they're not moving up to a high energy level, falling back down and giving off radiation. But then if you take, for example, white light and you pass that through this gas, okay, that contains these specific types of atoms, and then what comes out the other side. So essentially what you're doing is when this light comes in, what's happening is the atoms are absorbing these wavelengths of light. And what happens then is when you pass then what's remaining through a prism and you split it up like this, you get this continuous spectrum. But what happens is these individual bands are absorbed. Those wavelengths of light are absorbed by the individual atom. And again, this is, so let's say this could be the spectrum for hydrogen, for example. Well, this is what hydrogen looks like if you excite the electrons in atoms of hydrogen, and when they give off light, they give off these specific wavelengths of light. Now, on the other hand, those same wavelengths of light, hydrogen atoms will absorb those same wavelengths of light. So what will happen is when you shine white light that contains all of the wavelengths of light, the hydrogen atoms are going to grab on and absorb these individual wavelengths that it likes. So it's going to suck those all up, if you like, and then what's going to come out the other, it won't absorb these other wavelengths of light, and what will come out the other side then is what's known as this type of setup here, which is an absorption spectrum. And again, this kind of goes back to this idea that I was talking about up here. If we take this, I'll just bring it down here. So atoms will only, so a way to think about it is the only way to get this electron up to this energy level is that if a very specific wavelength of light hits that hits that electron, for example. So what you might say is that, for example, when the electron moves from here up to here, it takes this wavelength of light to get it to move up from here to here. If you want the electron to move up to this energy, second energy level, it takes this wavelength of light, which has a very specific amount of energy associated with it, to get it to move up from here to here. And then you'll also have higher and higher energy levels as well. So that's kind of like a way to kind of link in the specific type of atom to the type of emission spectra it produces, and then the type of absorption spectrum it produces as well. So another way to kind of think about it as well is, imagine these are hydrogen atoms, okay? And imagine I take this, so I just isolate, let's say, this wavelength of light, which is related to the color red. So imagine this wavelength the wavelength will be roughly about 700 nanometers. So imagine then, so I shine this, so imagine from here to here is 700 nanometers. So it's a specific wavelength of light that relates directly to this color here that we have. So it relates directly to the color red. And these are your hydrogen atoms. So hydrogen, H2. So when this light comes into contact, when it comes into contact with this atom, what will happen is the electrons will get excited, they'll move up, move back down again, and then it'll give back out this same wavelength of light. So it'll give this same wavelength of light back out the other side. And then if you pass that through a prism, and then you have a spectra here, what's going to happen is it'll give you this specific band, just like what we see here. So the electrons within this hydrogen atom will get excited when for example, when this wavelength of light is shone at it. Now, if I was to take, let's say, a wavelength of light from, let's say, here. So imagine then this is my other wavelength of light, and I get this wavelength of light and I shine it at my atom of hydrogen. So imagine this is the other wavelength of light, and it's somewhere down here. Let's say it's 500 nanometers. So let's say this is 500 nanometers. What will happen is that it'll just pass straight through, and it won't, the atom won't even absorb it. It'll just pass straight through, and it'll just show up on your spectrum like this. Okay, so it hasn't been emitted, or it hasn't been absorbed by the hydrogen atom. And the same then as well, like if you have, if I shine yellow light, for example, wavelengths of yellow light, these atoms will absorb that yellow light and then emit it back out again. And the same then with, these very specific wavelengths of light. All of the other light will just pass straight through, so everything that's in between the bands, that light will just pass straight through the atoms and then come out the other side and form, form this kind of a spectrum here. So that's another kind of way to think about it. So what we mean by that then is that, why does hydrogen only absorb these particular wavelengths of light? It's got to do with the electronic construction or the way that the electrons are arranged within an atom of hydrogen. And that's why some atoms will give off and absorb certain wavelengths of light while other atoms won't. Now, what we can actually do then is we can use what's known as an atomic absorption spectrometer. And we can use this device to actually measure the quantity or how much of, or the concentration of a particular atom that's present within a sample. So imagine So imagine this is my, so imagine I have a detector here like so, okay, and then I have this light source that can give off, let's say it sends out this very specific wavelength. So it's just sending off, let's say 700 nanometers light. So in other words, it's only giving off one type of light, and that one type of light is like a red light that has its wavelength is 700 nanometers. Now I know that hydrogen atoms will absorb this light and other atoms will not. So we say this is our light source. So this here is our light source, and then this here is our detector. So this is our detector. Now when there's nothing in front of this, the light is just passing through, you're getting 100%. So let's say all of the light, all of this red light is passing and being picked up by the detector. Now what we can do is we can have this same kind of setup, and then we can take our sample. This is our sample. So imagine this, inside this like container, you have hydrogen atoms. So you have hydrogen atoms, and then you have your detector here, like so. So again, what I do is I take this light and I pass it through. So 100% of the light is coming through. And then what happens is let's say what might be coming out is only 50%. So 100% of the light is going in, but what's actually coming out and being detected is only 50%. So there's a drop in 50%. Or another way to think about it is 50% of these wavelengths of light have been absorbed, and then that leaves 50% going through. So what we can say then is we can actually work out the number of hydrogen atoms present. So for example, if we let's say as we increase, so as the concentration of hydrogen atoms goes up, the amount of light being detected at the detector goes down. So decreases. And what we can do is then this is the basis of what's known as atomic absorption spectrometry, where we use these devices called an atomic absorption spectrometer. So what we can do is we can shine the light here, see how much of the light gets absorbed by the sample, find out how much of the light actually gets through and is detected, and then from that we can work out the number of atoms that are present. The more hydrogen atoms that are present, the bigger the drop in the amount of light being detected by the detector. And this happens because the hydrogen atoms are absorbing, for example, this very specific wavelength of light that I'm trying to shine through. So that's the basis of atomic absorption spectrometry. Atomic absorption spectrometry is particularly useful in the analysis of heavy metals. So for example, they can be used to test for heavy metals in blood, for example, and different things like that. So that is what we mean by, so that's like, these are what are known as absorption spectra, and then we just finished off and talked about the other different types of emission spectra that can be produced. So you can get atoms that give off wavelengths of light that are up within the ultraviolet region, and other ones that are down within the infrared region as well. So hopefully that makes sense, and thank you for listening.